In the next series of videos, I'm going to try to walk through the entire Calculus 1 exam review. So this may take several videos. I'll try to keep each one to about 20 minutes in length, and I'll try to specify within the video title which questions will be covered. Since we don't have a traditional exam schedule this year, and since I won't see you very many times, in fact, some of you will only see one more time before the final exam, I think this is a good way to present the content and to address many of your concerns. If you do have further concerns or questions after watching these videos, please reach out to me, send me an email or a message through Schoology, and we'll try to address those as they come up. So here we go with problem number 1. This is about evaluating limits using a graph. So if we try to answer part A, we shouldn't really encounter any questions here. The function evaluated at -3, well, we come to -3 on the x-axis, and we try to identify the y result. In this case, that does equal 5. However, for other x values, such as 0 and 2 and 3, we encounter a bit of a problem when doing that. And so that's where limits often help. You should recall that a limit describes the behavior of a function as x approaches some value, either from the left or from the right, or as a combination of both the left and the right. So this little minus sign, of course, means we're approaching the x value of -3 from the left. This plus sign means that we're approaching -3 from the right. And the lack of a symbol here is asking about the limit as we consider both the left and the right-hand direction. Now in this particular case, we had no trouble finding the function value at -3. So we typically wouldn't need to consider the limit, but as an exercise, that's exactly what we're doing. And as it turns out, when we approach -3 on the x-axis, from the left and from the right, the y values tend towards the same value, this positive 5. So as x gets larger and larger from below -3 on the x-axis, the y value gets closer and closer to 5. And as x gets smaller and smaller and smaller, the y value also approaches 5. So in both cases, we would say the limits are equal to 5. And when the left limit and the right limit agree, that's when we can answer this question. Both the limits approach the same value, so we would say the limit altogether is equal to that value. If the left-hand limit and the right-hand limit disagree, then we would say that the limit itself does not exist. While we may have a left-hand limit and a right-hand limit individually, it is possible for the combination of the two to not exist. And we see that in the next row. So I'm going to pause the video now and ask you to complete the remaining questions on your own, and you can resume playback in a moment to check your work. And so these are the results that I would expect you to come up with for the remaining questions. At times the limits did not exist. That happened twice. At one point, the x value was undefined. I'm sorry, the function result was undefined at the provided x value. And the others, I think, were pretty straightforward. So if you have questions on those, please let me know. Now, a direct correlation to this notion of limits and function values is continuity, and we have a continuity checklist that we use to verify if a function is continuous at particular points. And the 3 points in that checklist are as follows. Number 1, the function has to be defined at a particular value, a. Number 2, the limit has to exist as x approaches that value of a. And then finally, the function value itself has to be equal to the limit value as x approaches a. So when we're identifying continuity, it's pretty easy to see that on a graph, a function is continuous as long as we can draw it without lifting up our pen or pencil. If there's a spot where we have to lift our pencil to continue to draw the shape, then that would identify a point of discontinuity. Of course, we would like to identify that specifically using definitions, and that's what we're going to do now. So at the point x equals -3, It appears that the function is continuous because I could draw that function without lifting my pen or pencil here. And if we consider the checklist, then we know that it's true. The function was defined, we know that the limit exists, and the limit is the same as the function result. So essentially each of these questions that were asked originally all are exactly the same. So we can say that at x equals 3, the function is continuous. But what about at 0? Well, when we look at 0 on the x-axis, it does look like there's a break in the graph, and there's no way that I can draw this graph without lifting my pen or pencil. So common sense tells us that the function is not continuous, but we should consult the checklist to verify. And as we look through this list, we see that we don't have an agreement in values across the board, and that's another good indicator that we have no continuity. And we can say that it's not continuous for a number of reasons. The function itself was not defined, so it looks like it fails checkpoint number 1, and that would be sufficient for us to move on. But also it fails number 2, that's worth noting. And consequently, if it fails 1 and 2, it would fail number 3 as well. But if you answer with either 1 or 2, I'd be happy with that. If you say that it fails all 3, that would be perfectly fine as well. Now at x equals 2, we do not have continuity, and at x equals 4, we do not have continuity. I'd like for you to explain why. Please pause the video now and check your answers in just a moment. At x equals 2, this graph actually passes the first 2 continuity checkpoints. The function is defined and the limit exists, but the limit and the function itself are not the same, so it failed checkpoint number 3. When x was equal to 4, the function was defined. It's actually the data point down here, but the left and the right-hand limit did not agree, so therefore the limit does not exist. We would say that it fails number 2. Now, identifying limits using a graph is one thing, and using tables is one thing as well. But we also have to evaluate limits based on algebraic concepts as well, and that's what's going to happen with these examples here. And generally speaking, when being asked to evaluate a limit using algebraic methods, the first thing we always should check for is whether or not we can directly substitute to find the limit. If we can't directly substitute, then we move on to factoring, and these two are by far the most common methods that we saw in this class. A more complicated form of factoring, if you will, is when we conjugate either the numerator or the denominator, and we sometimes encounter that. And then lastly, after we learned about our derivative rules, we were introduced to the L'Hopital method. Now, L'Hopital method was one that we did not spend very much time on at all in this class. So it may be a technique that you'd want to watch another video on by doing a search online. In part A, it looks like direct substitution will work just fine. There's no problem substituting the number 2 in place of this function. And after doing so, we see that the limit result is 7. The function tends towards 7 as we approach 2 on the x-axis. For part B, the direct substitution does not work, so we would resort to factoring. And since we factor the numerator as a difference of squares, we see that the factor x minus 5 can cancel with the factor x minus 5 in the denominator. And with that gone, we would say that the limit as x approaches 5 of x plus 5 can be directly substituted, and we see that 5 plus 5 is 10. Please keep in mind that your limit notation should be retained throughout all of these steps until the point where you directly substitute. Some of the spaces left on this practice exam or practice test or review is getting to be a little bit tight, so it might be worthwhile to jump off the page to a separate sheet of notebook paper to complete the remaining questions. And I'm going to do that for part C and D over here off to the right-hand side. In both of these cases, we cannot directly substitute because we would end up with a 0 in the denominator, so we have to use some other technique. In part C, we can't really factor either because of this square root sign. Factoring with square roots is a bit of a challenge. So I would try guessing method number 3 here, and I would multiply by a conjugate. Now, this is, again, a technique that wasn't used all that often. I think we only saw this in some Math Excel questions, but the process is fairly common. The goal here is that if we multiply by a conjugate of the numerator or the denominator, we might get to a point where we can directly substitute or perhaps factor further. Now, it's the numerator that's causing the problem here, I think. And by problem, I mean that's what's preventing us from factoring. So let's see what happens if we multiply by its conjugate. So the square root of x plus 3 stays as it is, and the 2 stays as it is, but instead of subtracting 2, I'm going to add 2. And as long as we multiply the numerator and denominator by the same thing, we're effectively not changing the expression, we're just changing the way it looks, because this fraction is really the same as the value 1. And in the process of multiplying the numerator, we essentially have to FOIL. So we get the square root of x plus 3 times the square root of x plus 3, and then it distributes as follows. Now, interestingly, when we multiply the radical x plus 3 times itself, we're left with just x plus 3. On the outside and on the inside, we get two of the same terms. One's a positive 2 times the square root of x plus 3, and the other's a negative 2 times the square root of x plus 3, and those cancel. And now we're left with the expression x plus 3 minus 4, which can be pretty nicely simplified. The denominator I did not bother foiling, and perhaps you can see why in just 1 second. X plus 3 minus 4 is x minus 1, and by leaving the x minus 1 factor in the denominator, then we're left with something that can be factored from the numerator. So x minus 1 and x minus 1 cancel, or factor. And now we're left with the phrase, the limit as x approaches 1, of 1 over the conjugate of the numerator. And that really couldn't have worked out better for us, because at this point we can directly substitute. We can substitute 1 in place of x now. And even if we couldn't have, oftentimes the simplification of this fraction leads us to another technique that we might have been able to use. So after we directly substitute, we see the square root of 4, which is 2, plus 2 is 4, and we're left with 1/4. So it appears that the limit of the original expression is equal to 1/4. In part D, I don't think a conjugate is necessary, but it is awfully nice, or it would be nice if we can eliminate some of these fractions. And so what I'm going to do is find a common denominator in the numerator of this complex fraction, and we'll do that by multiplying by various forms of the number 1. In this case, 2 over 2 and x over x will produce a new denominator of 2x. Now, there's no guarantee that this will work, but oftentimes if we simplify the expression or combine like terms whenever possible, we do find ourselves in a position where some good things can happen. Now, I'm completing 2 steps at once here. I know that the common denominator is going to be 2x, and the result of the products of these numerators are going to subtract. So I have 2 minus x in the numerator of the numerator, and now 2x in the denominator of the numerator. At this point, I recognize that 2 minus x is awfully similar to x minus 2, so I might try doing this next. I'm going to factor out a negative 1. And doing so, factoring out a negative 1 from this term is going to allow me to reverse the order of that subtraction. If this was an addition problem, we wouldn't have to worry about that. And I'm also making a mental note that it's this upper numerator that's being divided by x minus 2. Now that phrase x minus 2 could be perceived as a fraction, x minus 2 over 1. And what this allows me to do then is to change this division problem to multiplication. And once we do that, if you haven't already spotted it, you should see something that's very helpful next. So we've got 1 times x minus 2 over 2x. We're going to multiply by the reciprocal. And hopefully you recognize that as we multiply these fractions, the x minus 2 factors will cancel. This leaves me with the expression negative 1 over 2x, which still may be a problem in some cases, but in this case it's not. We can directly substitute at this point because 2 is not causing a problem in the denominator, only the number 0 would be causing a problem in the denominator. So if we directly substitute at this point, we can say that the limit as x approaches 2 is negative 1/4. Now in part E and F, we're going to use a technique called L'Hopital's rule. And L'Hopital's rule states that if you're looking for the limit as x approaches some value of one function that's being divided by another function, so if you've got a quotient of two functions, well, that limit is actually equal to the limit as x approaches the same value of the derivative of each function. So if you can't determine the limit using traditional techniques of this fraction, then find the derivative of the numerator and the derivative of the denominator and try to find the limit of those. And if that doesn't work, then try it again, because you can use the derivative of a derivative a second time. So essentially you're looking at the second derivatives of functions and so on. In the interest of time, I'm not going to complete part E, but hopefully you can see where that might go. This doesn't look like we can directly substitute. We can't use a conjugate. We can't use simple factoring techniques. But if I take the first derivative of this expression, well, at least the denominator, if I take the first derivative of it, and I will have to take the derivative of both, that's going to give me a new fraction, but the derivative of the denominator is 2x, which still can't be directly substituted, but if I were to take a second derivative, I'd be left with just the number 2, and I'd be looking at a pretty complicated derivative in the numerator, but at least it's something that we could directly substitute with the number 0. Well, I should say we should most likely be able to substitute it. When we start taking the derivative of tangent, we might encounter something interesting. I may have to try that on my own off screen. I don't have the time to do it, or I don't want to take too much time doing that one in this particular video. I'd like to get through this limit and still keep this video at or around 20 minutes. But if we try walking through part F, hopefully you'll see a better opportunity to see how L'Hopital's rule works. So what we're going to do here is take the derivative of both the numerator and the denominator, because clearly I can't substitute the number 0 into this expression in the denominator. Now in the numerator, the derivative of 1 is 0. We'll subtract the derivative of cosine, which is negative sine of x. And in the denominator, we needed to use the product rule. So the derivative of the first function times the second function plus the first function times the derivative of the second, that is. And after we simplify, we get this expression, and you might be thinking to yourself that that didn't do any good because we still have x times cosine of x, which is going to turn to 0 in the denominator. But what we have to remember is that that's just one piece of the denominator now, and when directly substituted, this becomes 0, but sine of 0, and I almost made a mistake here. I almost said that sine of 0 is 1, but I'm going to make a mistake by doing that. So I think L'Hopital's rule a second time might be necessary here, and I chose this problem because I didn't think that would be the case, but it looks like it might be. So the derivative of sine of x is cosine of x, and the derivative cosine x. And so here we have the derivative of the second function, derivative of the first times the second, plus the first times the derivative of the second. So again, we needed to use the product rule when finding the derivative of this group. Here again, it may be tempting to try factoring out cosine because it occurs in both the numerator and the denominator. But recall, we can't do that because the denominator terms are separated by addition signs. Now we can combine these two like terms. We've got 2 cosine of x's, but we still have an addition of a secondary term, x times negative sine of x, or we could say minus x times sine of x. Now here's the point that I was going to make a moment ago. We still have 0 times something in the denominator. This is going to create a 0 value. However, it is just a 0 in one location. When we evaluate x at 0 in these other positions, we do get a calculated result, and we're going to be in much better shape. So if we directly substitute, we would see cosine of 0 divided by 2 times cosine of 0 minus 0 times sine of 0. And while 0 times sine of 0 does cancel itself and disappear because it is equal to 0, cosine of 0 is equal to 1. And so what we're left with is 1 over 2 times 1, or 1/2. And so that example utilizing L'Hopital's rule really wasn't all that bad. I would anticipate that the derivatives using L'Hopital's rule in Part E might be a bit more challenging because you do have to use the chain rule in the numerator. But I'm going to pause the video, or stop this video for now, and pick up with the next page of review in the next video. When you try Part E, go ahead and do that on your own, and you can check your work with an online limit calculator, or you can come see me for extra help or clarification. Thanks for watching.